Go outside, tilt your head back, and find Orion. You'll know it immediately. 3 stars in a perfect diagonal line. Orion's belt, cutting across the winter sky like a cosmic arrow someone drew with a ruler. And in the upper left corner of that familiar shape, burning with a color that is unmistakably, almost stubbornly red, there is a star. That star has a name. Betelgeuse. Say it out loud. Betelgeuse. Yes, like the movie. Tim Burton didn't pick that name by accident. There is something in that word that sounds ancient, enormous, and slightly dangerous. Because that is precisely what Betelgeuse is. Ancient. Enormous. And right now, in 2026, more interesting than it has ever been in the entire history of human astronomy. Not because it just exploded. It didn't. And anyone telling you it did in 2026 is selling you something. What happened in 2026 is something different. And in some ways more fascinating, we discovered that Betelgeuse is not alone. After decades of suspicion, of indirect hints and mathematical whispers, we finally found proof. There is a second star orbiting Betelgeuse. A companion, small, young, embedded deep in the outer atmosphere of a dying giant, orbiting it the way a bracelet circles a wrist. Her name is Siwarha, and her discovery doesn't just explain decades of mysterious behavior from Betelgeuse. It changes what we think the explosion will look like when it finally comes. It raises questions no one had thought to ask before, and it turns what was already the most anticipated stellar event in modern history into something genuinely, unexpectedly stranger. This is that story. Wide shot, Orion constellation time-lapse. Betelgeuse pulsing visibly red at upper left. Before we talk about what's happening now, we need to establish what Betelgeuse actually is, because the numbers involved do something to your brain if you let them in properly. Our sun is a star. An average star, a medium-sized star by the standards of the Milky Way. It is 864,000 miles in diameter. If you replace the Earth with a marble, the sun would be roughly the size of a large beach ball sitting 6 feet away. That is already incomprehensibly large. The sun contains 99.86% of all the mass in the entire solar system. Everything else, all 8 planets, all their moons, all the asteroids, all the comets, the entire Kuiper belt, is the remaining 0.14%. Now Betelgeuse. Animation, solar system to scale, then Betelgeuse dropping in over the center. If you remove the sun from the center of our solar system and place Betelgeuse there instead, its surface would extend past the orbit of Jupiter. Jupiter orbits 484 million miles from the sun. The surface of Betelgeuse, not the outer atmosphere, the actual visible surface, would engulf Mercury, Venus, Earth, Mars, the asteroid belt, and reach to Jupiter. Earth would be deep inside the star. You would not be orbiting it. You would be inside it. Its volume is large enough to hold over 400 million suns. 400 million. And yet, here is the paradox that makes astrophysicists smile. Betelgeuse is only about 16 to 20 times more massive than the sun volume of 400 million suns, but mass of only about 16 to 20. How? Because Betelgeuse has bloated outward into an evolutionary phase called a red supergiant. The outer layers have expanded so enormously that their density is thinner than the best vacuum we can create in a laboratory on Earth. You could walk through the outer layers of Betelgeuse if you had some way of surviving the plasma and the radiation, and encounter almost nothing. The center is a crushingly dense nuclear furnace. The exterior is nearly nothing, spread across a sphere larger than Jupiter's orbit. This is a dying star wearing a costume that makes it look enormous. The swollen exterior is a symptom, not the whole story. The story is what's happening in the core. Cut to stellar interior animation, layers of nuclear burning shown in concentric shells, stars live by burning. That is not a metaphor, it is a precise physical description. At the core of a star, temperatures and pressures are so extreme that atomic nuclei, which under normal conditions repel each other because they carry the same positive electrical charge, are forced together violently enough to fuse. When they fuse, they release energy. That energy is what holds the star up against its own gravity. Stop the fusion and gravity wins. The star collapses. Our sun burns hydrogen. In its core, 4 hydrogen nuclei fuse to form 1 helium nucleus, and the tiny difference in mass between the input and output is converted directly into energy via E equals mc squared. Every second, the Sun converts 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons becomes sunlight. The sunshine that grows your food, powers your weather, warms your skin on a summer afternoon. That is 4 million tons of matter converted to energy every single second for the past 4.6 billion years. The Sun has enough hydrogen fuel to keep this up for another 5 billion years. Betelgeuse had the same fuel, but it started with much more mass, and more mass means hotter core temperatures, which means faster burning. Betelgeuse burned through its hydrogen supply in roughly 2 million years, a fraction of the Sun's main sequence lifetime. Then, with no more hydrogen in the core, the furnace sputtered. Gravity compressed the core. The compression heated it up. And at those higher temperatures, helium ignited. Helium fusion produces carbon and oxygen. When the helium ran out, carbon burning. Carbon produces neon, sodium, magnesium. When carbon ran out, neon burning. Then oxygen. Then silicon. Each successive stage burns hotter, faster, more desperately, and produces heavier and heavier elements. The silicon burning phase, the final stage, produces iron. Iron is where it ends. Iron will not release energy when it fuses. Iron is the most stable nucleus in the periodic table. Fusing iron costs energy rather than releasing it. So when the core of a massive star fills up with iron, the nuclear furnace goes cold. There is no next stage, no backup fuel, no emergency system. The fire simply stops. And what happens next happens in less than a second. Animation. Iron core collapse. Shockwave propagating outward. The iron core, which has been accumulating for months to years at the end of silicon burning, reaches a critical mass, about 1.4 times the mass of our Sun, compressed into a sphere about the size of Earth. At that moment, the quantum mechanical pressure holding the core up against gravity fails catastrophically. Electrons are forced to merge with protons. They become neutrons. An enormous burst of neutrinos is released, and the core collapses from the size of Earth to a sphere about 20 to 30 kilometers across in roughly a tenth of a second. The city of Los Angeles is about 50 kilometers across at its widest point. The collapsed remnant of a star that once held 400 million suns would fit inside half of Los Angeles. The infalling outer layers hit this newly rigid neutron core like a wall. They bounce. A shockwave, one of the most energetic events in the known universe, propagates outward through the entire stellar envelope at a significant fraction of the speed of light. The star tears itself apart from the inside out. That is a supernova. Betelgeuse has been in the red supergiant phase for roughly 100,000 years. It could remain there for another 100,000 years. Or it could have already crossed the threshold. We genuinely do not know. Graphics, uncertainty range timeline, from now to 100,000 years. Here is the honest state of the science. A study published in June 2023 analyzed the pulsation periods of Betelgeuse and concluded that the star appears to be in the late stages of core carbon burning, the penultimate fuel stage before silicon, before iron, before collapse. The carbon burning phase for a star like Betelgeuse lasts roughly 1,000 years. If that analysis is correct, the supernova could be anywhere from a few hundred to a few tens of years away. The scientific community received this with measured interest and considerable caution. The error bars on stellar evolution modeling are enormous. We cannot look inside Betelgeuse's core. We infer what's burning there from the star's pulsations, spectrum, and luminosity, like trying to diagnose what's happening inside a building's boiler by listening from across the street. The consensus view among the broader astrophysics community remains that Betelgeuse will most likely go supernova somewhere in the next 100,000 years. But most likely in the next 100,000 years does not mean not in your lifetime. The probability that it explodes in any given century is low. The probability that it explodes in the next few centuries is not negligible. And the history of science is littered with events that happened earlier than models predicted. What we can say with absolute certainty: Betelgeuse will explode. The question is only when. And then, in January 2026, we discovered something that made the when question simultaneously harder and more interesting to answer. Cut to Hubble Space Telescope imagery, then Harvard CFA footage. For years, quietly at first, then more insistently, a small group of astronomers had been arguing that Betelgeuse's behavior didn't quite add up. Here is what everyone knew. Betelgeuse is a variable star. Its brightness goes up and down on a cycle of roughly 420 days. This is expected. Red supergiants pulse. They breathe, expanding and contracting, the outer layers oscillating as pressure and gravity trade off. This pulsation, occurring within Betelgeuse's core, was found to be typical of red supergiant stars. But there was a second cycle, a longer one, about 2,100 days, roughly 6 years. This longer variation did not fit neatly into any model of simple stellar pulsation. Some researchers proposed large convection cells on the surface, or magnetic activity, or shifting dust clouds in the surrounding envelope. These explanations were plausible, but they were uncomfortable. They felt like explanations invented to plug a gap rather than explanations derived from first principles. The more elegant explanation, the one that kept reappearing at the edges of the literature, was a companion star. If something was orbiting Betelgeuse every 6 years, passing through its extended atmosphere, its gravitational influence would produce exactly this kind of longer period brightness variation. The math worked, the physics was clean, but without direct evidence, it remained theoretical. The idea had been gaining traction for years. In September 2025, the International Astronomical Union's Working Group on Star Names took the unusual step of officially recognizing a name for this still unconfirmed companion, Siwarha. The name derives from Arabic, meaning her bracelet. Appropriate, since Betelgeuse itself means the hand of Al-Jawza. In Arabic, the ancient name for what we call Orion. The bracelet circles the hand. They named a star they had not yet proven existed. That takes a particular kind of scientific conviction. Graphics, orbital diagram, Siwarha's path around Betelgeuse over 6-year period. 4 months later, at the 247th meeting of the American Astronomical Society in Phoenix, Arizona, January 2026, Andrea Dupree of the Harvard Center for Astrophysics stood before a room of colleagues and presented the results of her team's 8-year study of Betelgeuse. They had found Siwarha's wake. Not the star itself, not its direct light, not an image of it as a distinct point. Siwarha is currently on the far side of Betelgeuse from Earth's perspective, eclipsed by the enormous red disk. But as Siwarha moves through the outer atmosphere of Betelgeuse, an atmosphere so vast and so tenuous it extends for many stellar radii beyond the visible surface, it creates a trail, a dense wake of gas, disturbed and compressed by the companion's passage, the way a boat's hull presses water into a churning wake behind it. Using 8 years of observations from NASA's Hubble Space Telescope combined with data from ground-based observatories at the Fred Lawrence Whipple Observatory in Arizona and the Roque de los Muchachos Observatory in the Canary Islands, Dupree's team tracked subtle changes in Betelgeuse's spectrum, the specific fingerprints of different elements in the star's light, and the velocities of gases in its outer atmosphere. The pattern that emerged was unmistakable. Every 2,100 days, exactly when Siwarha's orbit would bring it past the near side of Betelgeuse relative to Earth, a trail of denser material appeared in the spectroscopic data. Ripples in the atmosphere, precisely consistent with a companion of roughly 1.5 solar masses plowing through the tenuous outer gas. It's a bit like a boat moving through water, Dupree said. The companion star creates a ripple effect in Betelgeuse's atmosphere that we can actually see in the data. With that, Betelgeuse went from being a solitary dying giant to a binary system. 2 stars locked in an intimate gravitational partnership, one vast and ancient and doomed, the other small and comparatively young, orbiting through the outer layers of its enormous companion every 6 years. Let's establish exactly who Siwarha is, because her nature matters enormously to what happens next. Animation, scale comparison. Sun, Siwarha, Betelgeuse. Siwarha has a mass of approximately 1.5 to 1.6 times that of our Sun. She orbits Betelgeuse at a distance of roughly 4 astronomical units, 4 times the Earth-Sun distance, which in our solar system would place her between the asteroid belt and Jupiter. Her orbital period is about 5.7 to 6 Earth years. Based on her spectral properties, She appears to be an F-type pre-main sequence star, meaning she is young in stellar terms, still in the early stages of her nuclear burning life. She is hotter and somewhat brighter than our Sun, burning with a yellow-white light that is completely hidden from us at the moment, swamped by the vast red glow of Betelgeuse. Think about what this means dynamically. You have Betelgeuse 8 to 10 million years old, in the terminal phase of its stellar life, its nuclear furnace burning through progressively heavier elements in progressively shorter stages. And orbiting through its outer atmosphere, every 6 years, is Siwarha, young, energetic, embedded in the gas and plasma of her dying companion, her own future measured in billions of years if left to her own devices. The orbital distance, 4 astronomical units, puts Siwarha deep within Betelgeuse's extended outer atmosphere on every pass. She is not orbiting at a safe distance. She is passing through the star. Through the outermost, most tenuous layers, yes, but through the star. The drag forces on her must be extraordinary. The transfer of material between them, Betelgeuse's stellar wind depositing gas onto Siwarha, Siwarha's gravity pulling on Betelgeuse's outer layers, is an ongoing, dynamic exchange. Some researchers have raised a scenario that is, depending on your perspective, either the most dramatic or the most tragic possible outcome. The two stars might merge before Betelgeuse reaches supernova. If Siwarha's orbit is decaying, if each pass through the dense inner atmosphere slows her slightly, reducing her orbital energy, then over time she spirals inward. A merger between a red supergiant and a companion star is not a gentle event. It would splash enormous quantities of gas outward in a luminous transient. A brief, bright eruption visible from Earth before the actual supernova, and dramatically alter Betelgeuse's rotation rate, spinning it up. And a faster spinning Betelgeuse produces a different kind of supernova than a slowly rotating one. Different explosion geometry, different remnant, potentially different distribution of the elements scattered into space. "We think the stars might merge even before Betelgeuse goes supernova," said Maxwell McLeod, one of the researchers studying the system. "This would splash out some gas, spin up Betelgeuse, and potentially affect the properties of the eventual supernova. Whether or not merger is the eventual outcome depends on the precise orbital decay rate, something we do not yet have accurate enough measurements to determine. What we do know is that Siwarha is currently on the far side of Betelgeuse, and is expected to emerge from behind it into our view in 2027. That emergence will be one of the most carefully watched astronomical events of the coming years. Multiple observatory teams are already planning observations designed to capture Siwarha's light directly, to resolve her as a distinct source, separate from Betelgeuse's overwhelming red glow. "Seeing the companion will be the ultimate proof of its implied existence," said Ed Guinan of Villanova University, a long-term Betelgeuse observer. "I can't wait." Cut to archival footage of Great Dimming news coverage, 2019 to 2020. We need to talk about the Great Dimming of 2019 and 2020, because it is one of the most dramatic recent chapters in Betelgeuse's story, and because the discovery of Siwarha has rewritten how we understand what happened. Between October 2019 and February 2020, Betelgeuse dimmed dramatically. Its brightness fell by roughly 60%, dropping from one of the top 10 brightest stars in the night sky to outside the top 20, visibly, noticeably dimmer than its neighbor Aldebaran. For a star known to pulse gently in brightness every 420 days, this was extraordinary. The dimming was sharp, unexpected, and deep. The internet responded as the internet does. "A giant red star is acting weird and scientists think it may be about to explode," ran one prominent headline. The New York Post declared it due for explosive supernova. Across social media, people were talking about a star, a specific star, one with a recognizable name, in a way that almost never happens outside of science fiction. The scientific community was more measured. Several teams immediately began intensive observations. And over the following months, a consensus emerged. The Great Dimming was caused by a massive ejection of material from Betelgeuse's surface. A cloud of dust, roughly the size of the Moon's orbit, was expelled from the star's convective outer layers, essentially a giant stellar burp. As this cloud expanded and cooled, it formed dust particles that blocked a portion of Betelgeuse's light from reaching us. By early 2020, as the cloud dispersed, the star brightened again. Not a supernova warning. A sneeze. Animation. Dust cloud ejection from stellar surface. Light curve showing the dimming. But here is the part the Siwarha discovery complicates. Andrea Dupree's team has found that the Great Dimming occurred almost exactly when Siwarha was making its closest approach to the near side of Betelgeuse in its 6-year orbit. The timing is not conclusive, correlation is not causation, as every scientist will quickly remind you, but the possibility that Siwarha's gravitational influence played a role in triggering the material ejection cannot be dismissed. The companion, pulling on the outer layers of the red supergiant as it passed by, may have catalyzed the largest outburst Betelgeuse has displayed in recent observational history. If that's true, then every 6 years, every time Siwarha completes an orbit, Betelgeuse may experience some version of this kind of gravitational perturbation. Some passes may be subtle. Others, depending on the precise geometry and orbital parameters, could trigger events more dramatic than 2019. We don't know yet. We are only now building the framework to understand what this binary system does over time. What we can say is this: Betelgeuse alone was already one of the most complex and behavior-rich stars we had ever studied. Betelgeuse as a binary system is something significantly more interesting. Wide shot, dark sky, Orion rising, person standing in foreground watching. Let us now ask the question that every person who hears about a nearby supernova eventually asks, and that deserves a thorough, honest answer. When Betelgeuse finally goes supernova, whenever that is, what will it actually look like from Earth? At 650 light-years, Betelgeuse sits at a distance that puts it firmly in the spectacular but safe category. Let's do the comparison properly. The full moon sits at a visual magnitude of about -12.7. Venus at its brightest reaches about -4.9. The International Space Station, passing overhead, briefly hits -5 or -6. A Betelgeuse supernova at peak brightness is estimated to reach somewhere between magnitude -8 and -12, depending on the actual energy of the explosion. At the lower end of that range, it would be significantly brighter than Venus, clearly visible in daylight as a distinct point of light if you know exactly where to look. At the upper end, it would approach the brightness of the full moon, absolutely, unmistakably visible in broad daylight without any effort, casting shadows at night, bright enough to read by. Simulation, comparison of night sky brightnesses, then shadow demonstration. Let's be specific about the shadow claim because it is the kind of thing that sounds like an exaggeration but is not. The threshold for an object in the night sky to cast visible shadows is roughly magnitude -6 or brighter. Venus at -4.9 can cast faint shadows under ideal conditions. A Betelgeuse supernova at magnitude -10 would cast shadows similar in sharpness to moonlight. You would step outside on a clear night, and the light from a dying star 650 light-years away would draw your shadow onto the ground beneath you. This peak would last for weeks, possibly 2 to 3 weeks at maximum brightness before beginning to fade. But the fade would be slow. After the peak, the supernova would remain easily visible to the naked eye for months. Based on SN 1987A, the supernova that occurred in the Large Magellanic Cloud, a satellite galaxy of the Milky Way in 1987, which was at 168,000 light-years, 250 times farther than Betelgeuse, the visible naked eye phase lasted nearly a year. A Betelgeuse event incomparably closer would remain naked eye visible for a year or more. For historical context, the supernova of 1006 AD, at 7,200 light-years, was described in Arabic, Chinese, European, and Egyptian records as visible in daylight and bright enough to cast shadows. It was 11 times farther than Betelgeuse. The 1054 supernova that created the Crab Nebula, 6,500 light-years, was visible in daylight for 23 days and to the naked eye at night for nearly 2 years. That is 10 times farther than Betelgeuse. We have no modern precedent for what an event at 650 light-years would look like. Nothing in recorded history comes close. The Betelgeuse supernova will be, by a very wide margin, the most spectacular astronomical event any living human has ever witnessed. The constellation Orion, as we know it, will be unrecognizable during peak brightness. The familiar pattern, the belt, the sword, the hunter's shoulders, will be overwhelmed by the blazing point at Betelgeuse's position. Children born during those weeks will grow up with their parents pointing at that light and explaining what it is. Artists will paint it. Photographers will shoot time-lapse of it nightly. Every telescope on Earth and in orbit will be fixed on it. And then, slowly, it will fade. And where Betelgeuse was, something new will appear, not to the naked eye but in telescopes. An expanding cloud of gas. The Betelgeuse Nebula. A growing, glowing structure that will, over the following centuries, become one of the most spectacular deep-sky objects in the Northern Hemisphere. Animation, neutron star formation, rapidly spinning pulsar with radio jets. What is left at the center of the nebula? Almost certainly a neutron star, possibly a black hole. A neutron star is one of the most extreme objects the universe produces short of a black hole. It is the collapsed iron core of a massive star, now composed entirely of neutrons packed so densely that a teaspoon of its material would weigh roughly 4 billion tons on Earth. It is 20 to 30 kilometers in diameter. It may be spinning hundreds of times per second, born spinning fast by the conservation of angular momentum during collapse, the way a figure skater spins faster when they pull in their arms. If the neutron star is oriented such that its magnetic poles, from which intense beams of radio waves are emitted, sweep past Earth with each rotation, we will detect it as a pulsar. A lighthouse of radio waves, clicking on and off hundreds of times per second, with the precision of an atomic clock. The Crab Nebula has a pulsar at its center. It spins 30 times per second. It was born in the 1054 supernova. It will keep spinning, slowing gradually, for millions of years before it finally runs out of rotational energy. If Betelgeuse's core mass is on the higher end of estimates, if the iron core that forms is massive enough that even neutron degeneracy pressure cannot hold it up, the collapse continues past the neutron star phase directly to a black hole. The neutron star forms briefly and then vanishes into a singularity, emitting a second burst of neutrinos as it does. In this case, there may be almost no visible optical signal from the collapse itself. The outer layers, lacking the energy input from a bouncing neutron star, might not explode as vigorously. This scenario, called a failed supernova in some models, is less certain and less likely for Betelgeuse's mass range, but it is not excluded. The dominant scenario is a neutron star, a pulsar at the center of a beautiful expanding nebula, in the constellation Orion, beating out radio waves into the galaxy for millions of years to come. Cut-to, animation of neutrino detectors, underground laboratory footage. Before the light arrives, something else does. Neutrinos are among the strangest particles in the universe. They have almost no mass, less than a millionth the mass of an electron. They interact with normal matter so rarely that they pass through virtually everything without disturbing it. Right now, as you watch this, approximately 100 trillion neutrinos from the sun are passing through every square centimeter of your body every single second. You feel nothing. They don't care about you. They pass through the entire Earth as if it isn't there. And yet, in the core of a collapsing star, conditions are so extreme that even neutrinos, the universe's most antisocial particles, interact briefly with the surrounding material before escaping. In the first 10 seconds of a core collapse, more energy is released in neutrinos than our sun will emit in its entire 10 billion-year lifetime. Not in light, in neutrinos. The neutrino burst from a supernova carries roughly 99% of the total energy of the explosion. The visible light we see, the spectacular event that lights up the sky, is just 1% of what actually happens. These neutrinos travel at essentially the speed of light. They leave the collapsing core immediately, before the shockwave has even made it to the surface. They travel through the entire stellar envelope, through thousands of kilometers of plasma, in seconds. And then they race outward, ahead of the light that will follow once the shockwave reaches the surface. Animation, neutrino burst timeline, core collapse to Earth detection. The light takes hours to escape from the star after the collapse. The shockwave needs time to travel from the core to the surface. The neutrinos escape immediately. At 650 light-years, this translates to a warning. The neutrino detectors on Earth would register a massive flood of events. Not the 1 or 2 a day they normally capture from cosmic background, but thousands in a matter of seconds, roughly 1 to several hours before the first visible brightening of Betelgeuse in the sky. We know this because it happened before. On February 23, 1987, a star in the Large Magellanic Cloud exploded. Supernova 1987A, at 168,000 light-years, 250 times farther than Betelgeuse, the neutrino detectors at Kamiokande in Japan, the Irvine, Michigan Brookhaven detector in the United States, and the Baksan detector in the Soviet Union collectively registered 24 neutrinos from the event. 24. From 250,000 light-years away, a Betelgeuse supernova would hit Earth's detectors with vastly greater intensity. The Ice Cube Neutrino Observatory in Antarctica, a cubic kilometer of instrumented Antarctic ice, the largest neutrino detector ever built, would register tens of thousands of events in seconds. Super Kamiokande in Japan would similarly be flooded. Juno in China, Hyper Kamiokande, currently under construction. All of these instruments would simultaneously record the same burst of neutrinos from the same direction at the same moment. Physicists have set up automated alert systems. When a neutrino burst matching the signature of a core collapse is detected by any of these experiments, an alert goes out globally within minutes. Astronomers would receive a notification. Something just happened in the direction of Orion. Point your telescopes now. You have approximately 1 hour before the optical brightening begins. 1 hour. It is not much, but for astronomers, having any warning at all, any advance notice to get instruments calibrated and pointed before the most spectacular event in modern observational history begins, is extraordinary. And what the neutrino data itself will tell us, independent of the light, is equally extraordinary. The temperature of the forming neutron star, the mass it accretes in the first seconds, the spectrum of neutrino energies, the exact duration of the burst. All of these encode information about the physics of core collapse at densities and temperatures we cannot reproduce in any laboratory. Betelgeuse's death will be the most informative experiment in astrophysics since the universe began. Graphics. Periodic table. Highlighting elements forged in stellar interiors. Now let us talk about why any of this matters beyond spectacle. You are made of carbon. Your DNA is a carbon-based molecule. The glucose your cells burn for energy is carbon-based. The proteins in your muscles, the lipids in your cell membranes, the neurotransmitters in your brain as you process these words, carbon. Beyond carbon, you are oxygen, the molecule you breathe and that saturates your blood. Nitrogen. Calcium, which is in your bones. Iron, which is in your blood. The iron in hemoglobin that carries oxygen to every cell in your body. None of these elements were made in the Big Bang. The Big Bang produced hydrogen, helium, and trace amounts of lithium. 3 elements. That is the entirety of primordial nucleosynthesis. Everything else, every element on the periodic table beyond those 3, was made inside stars. Carbon, oxygen, and nitrogen, produced in the helium burning and later phases of massive stars. Calcium. Silicon burning in stellar cores. Iron. The final nuclear burning stage before collapse. These elements were not available in the universe until the first generation of massive stars lived and died. Until they made these elements in their cores and scattered them through space in their deaths. Animation. Supernova remnant expanding. Material mixing with interstellar gas. New star formation. A supernova like the one Betelgeuse will eventually produce will scatter roughly 10 solar masses of processed, nuclear-enriched material into the interstellar medium. Carbon, oxygen, silicon, sulfur, iron, and elements heavier than iron, gold, platinum, iodine, the elements that require the intense neutron flux of a supernova itself, or of neutron-star mergers to be produced, scattered outward at tens of thousands of kilometers per second, eventually slowing, cooling, mixing with the ambient gas of the galaxy, becoming part of new molecular clouds, new protostellar nebulae, new solar systems. The atoms in your body were forged in a star that died before the sun was born. The iron in your blood passed through a supernova. Not metaphorically, physically. The individual iron nuclei in your hemoglobin were produced in the silicon-burning phase of a massive star, released in its explosion, dispersed into the interstellar medium, and eventually incorporated via the molecular cloud from which the solar system formed 4.6 billion years ago, into the Earth and through geological and biological processes into you. Betelgeuse is not a distant, unrelated event in the night sky. It is a predecessor, a system that did exactly what the star that made your iron did, and when Betelgeuse eventually explodes, it will contribute its own processed material to the galaxy's reservoir. Somewhere billions of years from now, in a solar system that does not yet exist, in a biology that we cannot imagine, there will be something alive that contains iron that once burned inside Betelgeuse. We are not separate from this process. We are part of it, downstream of it already, upstream of whatever comes next. Cut to Historical Records Montage. Chinese Astronomical Scrolls, Tycho Brahe's Records, 1054 Supernova Rock Art. Astronomy has always driven civilization. The ancient Chinese astronomers who documented the 1054 supernova, recording its position relative to the crescent moon, noting its color, tracking its brightness night by night in meticulous detail, were doing something that seems on the surface practical. Cataloging the sky, noting anomalies, building the database that would help navigate ships and set agricultural calendars. But underneath the practicality was something more fundamental. They were responding to the sky changing. Something was different. And humans, since long before writing existed, have responded to the sky changing by paying very close attention. When Tycho Brahe observed the 1572 supernova in Cassiopeia, it shook European cosmology to its foundations. The Aristotelian model of the universe held that the heavens, above the moon, were perfect, unchanging, eternal. And here, in the perfect eternal heavens, a star appeared where none had been before, blazed for months, and disappeared. Brahe's careful measurements proved that the new star was far beyond the moon, in the region that was supposed to be immutable. If the heavens could change, the cosmological framework was wrong. This observation, a supernova, a dying star, contributed directly to the chain of intellectual events that produced the Copernican revolution, the birth of modern astronomy, the scientific method as we understand it. A star died, and from its death a worldview was born. What will the Betelgeuse supernova do to human culture in 2026 or whenever it finally comes? We live in an era of unprecedented self-absorption, social media feeds optimized to keep attention on the personal, the proximate, the immediately gratifying. The field of view has narrowed. And then one night, the sky changes. Something blazing appears in Orion that was not there yesterday. Something bright enough to cast your shadow. And it does not care about your feed. It does not ask for your engagement. It simply burns 650 light years away, sending light that left it before Columbus was born toward your eyes at this specific moment in history. Pause. Slow zoom on Betelgeuse. There is a documented psychological phenomenon called the overview effect, reported by astronauts who have seen Earth from orbit. The sudden, visceral comprehension of scale produces a cognitive shift. The ego recedes, the tribalism quiets, the sense of connection to something larger than any individual concern becomes overwhelming. Most of us will never go to space, but a Betelgeuse supernova, visible to every human being on Earth with clear skies, in the northern and southern hemispheres, requiring no telescope, no scientific training, no access to any technology, would deliver a version of that shift to the entire population of the planet simultaneously. We cannot predict what that does, but it would be something. It has always been something. Every time the sky has dramatically changed, we are pattern-recognizing, meaning-seeking animals who evolved under an open sky. When the sky speaks loudly enough, we listen. Animation. Siwarha orbit. Timing of 2027 emergence. Back to Siwarha, because her immediate future is something we will be able to watch unfold. She is currently behind Betelgeuse from our perspective, eclipsed, hidden. Based on orbital calculations, she will emerge from behind Betelgeuse into our view around 2027. Multiple observatory teams are already preparing for that moment. The James Webb Space Telescope, with its extraordinary infrared sensitivity, is one of the instruments best positioned to attempt a direct detection of Siwarha's light, separated from the overwhelming glare of her enormous companion. What they find will tell us enormous amounts. Siwarha's confirmed spectral type, whether she is truly an F-type pre-main sequence star as current indirect evidence suggests, or something different. Her precise mass, refined from the direct light measurements. Her luminosity, whether there is evidence of material transfer between the two stars, whether Betelgeuse's stellar wind is actively dumping mass onto Siwarha, altering her evolution, potentially making her brighter and heavier over time. Whether Siwarha's orbit shows signs of decay that would support the merger scenario. And perhaps most practically, The orbital parameters we derive from watching Siwarha's 2027 emergence will give us a much more precise picture of the binary system's dynamics, which feeds directly into our models of how and when the supernova will occur. Siwarha's discovery was not just an isolated finding. It was the opening of a door. We had been studying Betelgeuse for decades as a single, isolated star. Now we know it is a system, a gravitational partnership with its own internal dynamics, its own history of interaction, its own trajectory that is shaped not just by what one star is doing internally, but by what two stars are doing to each other. Graphics. Before and after. Single star model versus binary system model. This is how science works. Not in steady incremental steps, but in periodic fundamental revisions of what we thought we understood. The history of astronomy is a history of finding that the universe is more complex, more interconnected, more dynamic than the previous model allowed for. Binary stars are not unusual. In fact, the majority of Sun-like stars in the Milky Way are in binary or multiple systems. The Sun, alone in its solar system, is actually the exception. We had assumed Betelgeuse was like the Sun in this respect. It isn't. It never was. Animation, light delay visualization, 650 light-years as a timeline. Here is a fact about Betelgeuse that I want you to sit with for a moment, because it is one of the most genuinely strange things in all of observational astronomy. The light you see when you look at Betelgeuse left that star approximately 650 years ago. You are not seeing Betelgeuse as it is. You are seeing Betelgeuse as it was in roughly 1376 AD. Geoffrey Chaucer was writing the Canterbury Tales. The 100 Years' War was being fought in France. The Ming Dynasty had not yet risen to power in China. That is the Betelgeuse you see tonight, its state as of 6.5 centuries ago. This means that Betelgeuse may have already exploded. Right now, at this moment, there may be a pulsar spinning at the center of an expanding nebula where Betelgeuse used to be. The supernova may have happened 500 years ago, 300 years ago, last year. We have absolutely no way of knowing. The information, traveling at the speed of light, is on its way. It will arrive when it arrives. We cannot hurry it. This is the condition of all astronomy. We study the past, not the present. Every star we observe is a time-delayed message. The farther away the object, the more ancient the message. The galaxy's JWST reveals at the edge of its sensitivity are not galaxies as they are galaxies as they were 1 or 2 billion years after the Big Bang 12 billion years ago. We cannot see the universe as it is now. We can only see what it was, at varying delays depending on distance. Betelgeuse's 650-year delay is, in cosmic terms, nothing. A local story, a message from the recent past. But even that brief delay contains the possibility of the most dramatic surprise in modern astronomy. Stepping outside one evening and finding that the sky has changed, because information that has been traveling toward you for centuries has finally arrived. Slow tracking shot. Night sky. Orion prominent. What happens to Orion after Betelgeuse is gone? During peak supernova brightness, the constellation is effectively unrecognizable. The blazing new star obliterates the familiar pattern. Where once the hunter's shoulder glowed with a characteristic reddish warmth, there is now a blinding point that overwhelms everything around it. Then the fade begins. Over months, the supernova dims. First below moon-like brightness, then below Venus, then into the ordinary stellar range, and finally, over the course of a year or more, below naked eye visibility. Orion reassembles itself. The belt stars Alnitak, Alnilam, Mintaka are still there. Rigel, the blue-white star marking the hunter's foot at magnitude 0.1, is unaffected. Bellatrix, safe, the stars of the sword, the stars scattered around the central figure, all still present. But the right shoulder is gone. Where Betelgeuse blazed for the entirety of human history, in every cave painting, every myth, every navigational chart, every child's first identification of a constellation, there is now, in binoculars, a faint expanding cloud. A ghost. A memorial in gas and light, growing larger year by year, decade by decade. Time-lapse animation. Nebula growth over decades and centuries. In 100 years, the Betelgeuse Nebula will be visible as a distinct object in medium-sized amateur telescopes. In 500 years, it will have expanded to a degree across faintly visible in binoculars under dark skies. In 1,000 years, it will be a sprawling, multi-degree cloud of glowing filaments, one of the showpiece objects of the northern sky. A crab nebula for the second millennium, but larger, closer, and more spectacular. And at the center of all that expanding gas, a neutron star, spinning, emitting, 20 kilometers across, the compressed remnant of something that was once large enough to swallow Jupiter. Something that burned for 8 to 10 million years and then died in less than a second. Something that made, in its lifetime, elements that are right now inside you. CUT-TO, scientists at observatories, neutrino detectors, JWST Operations Center. Let's spend a moment appreciating the extraordinary moment in observational history we occupy, because it matters to how we will witness whatever Betelgeuse does next. The James Webb Space Telescope, operational since 2022, is the most sensitive infrared telescope ever built. It has already fundamentally challenged models of early galaxy formation, discovering massive, well-structured galaxies at redshifts that suggest they formed astonishingly early in cosmic history. When Betelgeuse's supernova occurs, JWST will observe it across a range of infrared wavelengths with a sensitivity that was simply impossible for SN 1987A in 1987. The evolution of the remnant, the cooling of the ejecta, the formation of dust in the expanding cloud, the emission from the central neutron star, will be traced in unprecedented detail. The Vera Rubin Observatory in Chile, conducting its legacy survey of space and time, will image the entire visible southern sky every few nights. Betelgeuse in the northern sky is not Vera Rubin's primary target, but the observatory's data will contribute to the global picture of the event, and its detection pipeline for transients, objects that change rapidly, will be one of the early warning systems. IceCube at the South Pole, Super Kamiokande in Japan, Juno in China. These neutrino observatories have been upgraded and expanded since 1987. Together, they form a global network that will capture the neutrino signal from Betelgeuse's collapse with a completeness and precision that will allow physicists to reconstruct the collapse itself. Not infer it from a handful of events, as they did with SN 1987A's 24 neutrinos, but trace it in thousands of events, building a detailed profile of what happened inside a collapsing stellar core in real time. Gravitational wave detectors LIGO, Virgo, CAGRA will attempt to detect the gravitational wave signal from the asymmetric mass distribution in the collapsing core. Core collapse supernovae are expected to produce gravitational waves, but the signal is expected to be complex and relatively weak compared to the binary black hole and neutron star merger signals these detectors have been designed around. A Betelgeuse supernova at 650 light-years would be the strongest gravitational wave source from a core collapse event ever recorded. Whether it is detectable above the noise is uncertain but possible. If it is, we will have simultaneous detection in neutrinos, gravitational waves, visible light, X-rays, gamma rays, and radio, a full multi-messenger picture of a stellar death. The people who built these instruments, the physicists who spent careers designing detectors, writing the software, training the graduate students, fighting for funding, running the experiments, many of them have said some version of the same thing. They built these instruments partly because of Betelgeuse, because they knew or hoped that in their lifetimes or their students' lifetimes, the star might go. And they wanted to be ready. That is its own kind of extraordinary. To build a machine, spend decades operating it, and wait, patiently, methodically, scientifically, for an event that might not come in your lifetime but that you want to be prepared for anyway. It is the most long-term commitment most humans ever make to a specific hope. Final section. Slow, measured tone. Let me be direct about something before we close, because clarity matters more here than drama. The title of this episode asked what happens when Betelgeuse becomes a supernova. The honest answer to when is, we don't know. Could be decades, could be centuries, could be tonight. The light from an explosion that already happened centuries ago could reach Earth at any moment. We genuinely cannot narrow it further than that with current tools. What we can say is that the 2026 discovery of Siwarha has transformed our picture of the system. We now know that Betelgeuse's behavior over the past decades, the great dimming, the longer 6-year brightness cycle, the asymmetric surface features, has been shaped in part by a gravitational partner we didn't know existed. This means every model we built of Betelgeuse as an isolated star needs revision. The timelines need re-examination. The expected properties of the explosion need recalculation. We are, in the most literal sense, starting over with a more complete picture. That is not a failure of science. That is science doing exactly what science does, finding that reality is more complex than the previous model allowed for, and building a better model. Final shot, Orion rising, Betelgeuse prominent, slow zoom. Here is what I want you to hold from this. Betelgeuse is 650 light-years away. The light reaching your eyes tonight left that star in the 14th century. It has been traveling through the interstellar void, through empty space that makes the vacuum of our best laboratories look crowded, for 650 years, and it arrives at your eye at exactly this moment. Not last year, not next year. Now, the iron in your blood was forged in a star that died before the sun was born. The carbon in your DNA was made in stellar interiors and scattered through space in explosions that predate the Earth by billions of years. You are not watching a distant, unrelated event when you look at Betelgeuse. You are looking at a cousin system, a massive star in the same galaxy, doing the same physics that produced the atoms you are made of in an earlier generation of stellar fire. When Betelgeuse finally goes, when the neutrino detectors ring simultaneously around the world, when astronomers send their alerts, when you step outside and find a second light blazing in Orion bright enough to make your shadow, you will be watching the universe do what it has always done. Burning the old to make the new. Dispersing atoms forged over millions of years back into the galaxy, where gravity and time and physics will eventually assemble them into something we cannot imagine. A neutron star will spin at the center of an expanding cloud that was once the shoulder of Orion's hunter. Siwarha will orbit alone, or merge into the remnant, carrying in her altered chemistry the trace of the giant she once circled. And the sky, after a year or a decade of fading, will reassemble into something almost familiar, Orion with a gap, a ghost where a star used to be, and in that space, slowly brightening over centuries, the most spectacular nebula our civilization will ever have a front-row seat to watch grow. We are alive right now. We have the instruments. We have the knowledge to understand what we're seeing. And we have, burning 650 light-years away, a star that has been building to this finale for 8 million years. Look up tonight. Betelgeuse is there. Red, ancient, and according to the latest science, not alone. What happens next is still being written. By physics, by gravity, by nuclear fire, by the universe that made you and that is still making things. We are watching.